Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Alright, so today we want to look at what the energy differences are between different wavelengths across the visible spectrum. So what we're going to do is start with our two edges of our visible spectrum here. Lambda equals 400 nanometers and lambda equals 750 nanometers. And in order to do that, we need to know what the energy is. So what we know is we know what our wavelengths are, we know constants. So our equation for energy is h, which is Planck's constant, times the frequency of the wavelength. And so we have our wavelength here, not our frequency. So we have another relationship here that is also hc over lambda, and c being the speed of light. So now what we want to do is figure out a way to just plug these numbers in. So some constants that I'm going to just write down values of, so I have them here. H is Planck's constant, 6.626 times 10 to the minus 34. Units on this is joules times seconds. C is our speed of light. This is our 3 times 10 to the 8th meters per second. And then another handy thing that will come in is Hc in electron volts times nanometers. Here is going to be 1240. It's electron volts times nanometers. And this here is a very handy relation to keep in mind in future if you are asked to find things for wavelengths in the visible spectrum in electron volts. So let's first look at what it is in electron volts. So the energy for the 400 nanometer wavelength is going to be Hc, which is 1240, divided by our wavelength, which is 400 nanometers. So let's look at the units here and make sure everything works out properly. I have nanometers canceling out, and all that is left is electron volts, so that is exactly what I want. This here gives me 3.1 electron volts. And this just gets plugged into your calculator as soon as the numbers are plugged into the equation here. So if we want to find the range, we now need to do the same exact calculation for our 750 nanometers. I'm going to go ahead and box this here, make it easy to figure out where it is when I'm comparing. So our energy for the 700 nanometer light, 1240 electron volts times nanometers divided by 750 nanometers this time. I'm going to rewrite that so it looks a little nicer here. Alright, so 750. Alright, and we want to do unit analysis again here. So nanometers and nanometers will cancel out, and I am left with electron volts. That is exactly what I'm looking for. And this here just gets plugged into the calculator again, and I get 1.65 electron volts. Alright, so in electron volts, you see our range here is our 1.65 electron volts to 3.1 electron volts. And I want to do the same exact thing, only now in joules. So I can either convert these, or I can just recalculate it using Planck's constant and the speed of light. And so I'm going to do the second way here. So E is H times C, so H 6.626 times 10 to the minus 34. And this is joules times seconds. And then our speed of light, 3 times 10 to the 8th meters per second. And I'm going to first calculate our 400 nanometer wavelength. So dividing by wavelength here is 400 nanometers. I'm going to convert that into meters because you can see there's meters here in our speed of light. So that is 400 times 10 to the minus 9 meters. So looking at units here, this is a little bit more complicated. There's a few more extra units. I have meters here and meters here, which will cancel out. I also have seconds and seconds that cancel out. So I'm left with joules, which is exactly what I'm looking for. So this just gets plugged into a calculator, and I'm given 4.97 times 10 to the minus 19 joules. And right there, gonna box that for you. And I need to do this one more time with a 700 nanometer light. So it's the same exact calculation, just plugging in a different wavelength. Planck's constant here, 6.626 times 10 to the minus 34. This is joules times seconds. It's the speed of light, which is 3 times 10 to the 8th meters per second. And divided by our wavelength, which is 750, translating it now into meters, so this is going to be times 10 to the minus 9 meters. So units here, I have meters and seconds both cancel out again, which is good. It means I wrote the equation the exact same way twice as far as units go, and I am left with joules. So the answer after plugging into the calculator gives me 2.65 times 10 to the minus 19 joules. All right, so